Okay, yes. So this first video that I'm making is going to be in relation to truss problems. So I'm actually going to work through this question 1 from the 2018 fall exam that was posted for you guys. I'm going to work through this question in its entirety using the whiteboard feature on Zoom. And then I'm also, after I finish up with that, I'm going to talk a little bit about question 1 on the 2019 exam that you guys also have, just to point out what is a little bit different with this problem as compared to the 2018 exam. So with this problem, I'm going to start by just sharing the whiteboard. So the first step with every truss problem should be finding our support reactions. In this case, we have a pin at point B and a roller at J. So we'll have the general truss shape with the members in between, but we basically have a force By, a force Bx, and a force Jy. How we would get these is we would include the external forces that are just on the drawing, and we would look at these in order to do a summation of forces and then also use moments. So we could say summation of forces in the x is equal to 0, and that's just equal to Bx plus 20 kips, which means that Bx is equal to negative 20 kips, or that Bx points this way with a magnitude of 20 kips. From here, we're looking at two unknown forces in the y direction, so we have to utilize a moment. I took the moment about point B, so that was going to need to equal 0, which showed us in a roundabout way. We had Jy as our unknown in the problem, and then these are all from the external loads that were placed on the truss. So we ended up being able to say that Jy was equal to 41.25 kips. And then from here, we can go back and utilize the summation of forces in the y to say that By plus Jy minus the two external loads, plug in the Jy that we found to get a By value that was 18.75 kips. So this process was relatively straightforward, finding the support reactions, and it should be, in most cases, you're going to need to utilize summation of forces in the x, summation of forces in the y, and some kind of moment. It's rare that you would ever see a problem where you didn't need to use all of them, because if you don't end up having forces kind of in that general setup, you end up getting a beam that isn't actually restrained. So now that we found our support reactions, we can move to the next part, which is where we kind of need to decide method of sections versus method of joints. In this case, we're going to use method of sections, and that tends to be the case that you'll use in these problems. The reason for it, more or less, is that method of sections is more useful and it will tend to be quicker because you're not having to go through each individual joint. So in this case, I would make a cut just to the left of that GH member, because when I was looking at the problem and seeing what the member actually looked like, I saw that if I made that cut, I would be cutting through the three members whose forces I'm actually interested in, EG, FG, and FH. So if I redraw the member with how it looks like, more or less, this is point K, here's point J for reference, and this point up here is G and H. So the forces that I have is I have these external forces. So this is 20 kips. This is Jy, which we found. And then there is a 40 kip force pressing down. And then now I just have to draw on the forces from the members that I cut through. So I'll have an EG, an FG, and an FH. Something that I want to point out here is the fact that all of these were assumed to be in tension. This is convention. Your professors hopefully talked about it in class. But the reason that this is useful is because when we eventually solve, if we get positive numbers for our forces, we know that something's in tension. If we were to get negative numbers, we can simply say, oh, okay, that means it's actually in compression. That's useful because this means we know that the positive and negative signs are always going to be tension compression. Whereas if, for example, you drew this arrow pointing the other direction for some reason, that would mean that these are actually flipped. I would just stick with this convention. Always draw your forces pointing away from the joint that they are coming from. So if I looked at that picture, there's a few things that I would want to pick out before I even started doing my force balances. The main thing is figuring out what is the angle for FG. So if I have FG like this, I'm looking for this angle. I would just be able to say that theta is equal to the tan inverse of 10/8. And this is coming from the problem geometry that's given. So I'm looking at a theta of approximately 51 degrees. From here, my next step would be to take the moment about mg. The reason for this is because this actually removes two of my unknowns easily because they're going right through g, leaving me with one unknown. So what I'm left with is the moment equation of negative fh times 10 plus jy times 8. Jy, if you remember, is one of our support reactions. We know it. So we're good to solve for FH is equal to positive 33 kips, which tells us that the member FH is in tension. Once we know that, the next piece that I would look at before I continue solving is knowing how FG splits into FGX and FGY. And that's as simple as saying, oh, okay, they're going to be the magnitude times the angle component. So for X, the way I drew my angle is I'm looking at cosine theta. For Y, I'm looking at sine theta. Technically, if you had drawn your angle, so if this is FG, I drew my theta here. If you had wanted to, you could have gotten an angle here, for example, which is alpha. And with alpha, we would be looking at FGX is equal to FG sine alpha. It won't matter. You just need to make sure that you understand what triangle you're drawing and how you're getting your angles. So using that, I can easily get myself a summation of forces in the y, set that equal to 0. It'll be jy, the external load of 40 kips, and the y component of fg, which how I defined it is fg sine theta. I'll end up getting fg is equal to the 1.6 kips when I plug in my jy. And once again, because it's positive, I know that this is in tension. And then the last piece for this section that I drew, I'm going to take the summation of forces in the x, set that equal to 0. So I'm able to say that 20 kips from the external load minus EG, which is what I'm looking for, minus FH, which we found in our first calculation, minus the x component of FG. So that's FG cosine theta. And if I go through and I solve this, I'm able to get that EG is equal to negative 14 kips. And this negative sign tells me that what EG is EG is equal to 14 kips of a compressive force. So this problem is almost complete. They're asking for the force on one more member, which is member JK. And with this, we end up more or less using method of joints, because what we're looking at is we're looking at point K, and I want to make my cut just to the left of that. So my forces end up being JK and IK. This theta value in here is the exact same as what we had used before, even though it doesn't end up being necessary to solve this problem. Just to note, what we're able to do is we're able to say a summation of forces in the y at point K is equal to 0. So we're able to say that 0 is equal to the y component of jk, which would just be jk sine theta. And what that tells us is that jk is equal to 0 and can also be called a zero force member. Zero force members can usually be found by inspection such as this, where we just said, hey, there's not going to be another force somewhere pointing in the y direction at any component in order to cancel out the y component from jk. So that was a problem from the 2019 exam. So I'm saving that to be able to share with you guys. And then if I X out of my whiteboard, there we go. And then I share the other problem just so I can note. So that was this problem right here from the 2018 exam. If we then look at the problem on the 2019 exam, this is going to be a similar thing. So we'll go through the same process where we're going to say, hey, let me find the support reactions. So in this case, that's going to be a by, a ky, and a kx. So we can find those. And then now they're asking us for forces in members dg, fg, fh, and gh. So I would start with a similar cut to the one I made in the last problem. And how I looked at this problem, as I said, I'm going to cut it here and look at this section to the right. The reason I did that is because this section still contains the GH that I'm interested in, while also having the DG, FG, and FH forces that I'm looking for. So once I make this cut, I can go through a similar fashion how I went through on the last problem that I showed you guys. And then where this problem differs is because they're asking for the force in that member GH, right? So we're not going to be able to make a cut that's vertical in any way to cut this member. We're going to have to make a cut that's horizontal somehow, right? One way that you can do this that I think is one of the easiest ways is if we just kind of make two cuts almost, but we connect them. So we can keep this original cut that we made, and now we can make a second cut and cut this way, right? And what this does is this allows us to use two known forces because both of these will still be included, and we know both of those from the original calculation. And now we have the GH that we want, and we have this HI. And how I went about solving this problem is I said, I don't care what HI is or what IH is, like that's irrelevant basically. So I thought to myself, I said, how can I not include that in any of my calculations? And we know that one way we don't have to worry about forces is if we take moments where they run through. So one way you can do that is to take the moment about, say, this point J. So if I think about what forces I now have to consider when I'm taking a moment, there's still our support reactions, but the only forces I'm going to have to consider are my Kx, my GH that I actually care about, and the Y portion of this FG, right? Because all of my other forces end up going through that point. So that's a quick tip. Most of these truss problems, the biggest thing is going to be making sure that you stay consistent, making sure you keep all your variables straight. Redraw your free body diagram every time, because if your free body diagram's right, your summation of forces equation should be right, your summation of moment equation should be right, and those are the biggest ways that you solve these problems.